Hello all, welcome back. Myself, I am Sai Krishna from the Department of Aeronautical Engineering from the Institute of Aeronautical Engineering. Today, I will be continuing with my course, that is aerospace propulsion. So, in this particular lecture, what we will be discussing is basically the nozzle theory. Understanding the nozzle is very critical in order to understand how the rocket actually works, in what way, particularly under thermodynamic reaction, in what way we can accelerate your exhaust velocity. Now, in your previous lecture, connecting to this, what you have derived is basically the thermodynamic relations of the nozzle as well as the thermodynamic equations, particularly thermodynamic thrust that has been derived. Now, continuing with that, first, in order to understand nozzle system, we'll first come with the ideal rocket propulsion systems, right? What propulsion system is considered as an ideal form? First, any concept of an ideal rocket is useful because can be used by basic thermodynamic principles which can be expressed with relatively simple mathematical relationships, right? We know the thermodynamic equations, all the four equations including zeroth law, first, second and third law, as well as few basic heat transfer techniques and few gas conditions. Now, these equations which describe quasi one-dimensional nozzle flows, right? If applied for a nozzle, these equations will describe for quasi, particularly 1D flows, and which represent a simplified idealization, right? Simplified idealization for a full 2 or 3 dimensional equations of real aerothermochemical behavior. Why? This term is basically air, heat and chemical. We are combining all three separate terms in order to understand the complex nature of your rockets, particularly nozzle reactions or nozzle flows, by considering a 1D state. Now, upon getting a 1D, you can just integrate the same over a period, over a dimension, in order to get a 2 or 3 dimensional equational form. Now, first, an ideal rocket, particularly rocket propulsion unit, is defined as one of which the following assumptions are valid. So first one will be the working fluid, right, which actually consists a chemical reaction of products, right? We are considering nozzle, right? A nozzle in which some flow occurs. Flow is basically on particular fluid, in our case a gas, right? Now gas, if you are breaking up clearly in more realistic way, a gas is nothing but my exhaust products, particularly chemical reaction products, right? So now the working fluid, particularly the chemical reaction products, should be homogeneous in composition. It means the composition around the section of a nozzle or the area through which we are considering should be the same. Next, all species, right? All the species of the working fluid are treated as gaseous, right? Any condensed phase, particularly liquid or solid, add negligible amount of total mass. Now, the working fluid in our case, which is nothing but our chemical reaction products, are considered as gaseous phase because upon combustion they are high pressure plus high temperature gases which are expelled through the nozzle, right, or expelled from the combustion chamber. Now, upon combustion, these products, particularly the fuel, whatever the fuel you are using, for example, liquid hydrogen or jet propellant or any other, and the oxidizer, particularly oxygen, are both upon combustion will convert themselves into gaseous form, right? These gaseous form are is a valid assumption that we are making through for considering a ideal rocket propulsion. Next, and one more thing, if any condensed phase, for example, any certain combination of rocket fuel, particularly liquid oxidizer as well as fuel will be giving out some amount of any condensed phases like liquid or solid phases of the material. So that will be considered as only a negligible amount to the total mass or total exhaust products that are being generated. Next, the working fluid. The working fluid, in our case, the combustion reacting products are or must obey the perfect gas law, right? The gas law accordingly. Next, there is no heat transfer across and all gas enclosure walls. Therefore, the flow is adiabatic. Adiabatic, in our terms, is basically there is no exchange of heat. Now, let us consider simple example. In a simple nozzle, while performing your 1D analysis, we are not considering regarding the material through which the nozzle is being made, but we are assuming that there is no heat transfer that is being taken place, so that the whatever energy that is being created at the end of or beginning of a combustion chamber or beginning of the nozzle is same throughout at the end of the nozzle also, right? Coming to the next assumption is there is no appreciable wall friction, right? There is no appreciable wall friction and all boundary layer effects may be neglected, right? There are no shock waves as well as other discontinuities within the nozzle flow. The shock waves, whatever are there, are formed outside of the nozzle in general, right? And whereas the discontinuities is the only one while creating a CD nozzle, right? A single discontinuity, which is called as throat, will be available in order to maximize my flow velocity, right? Regarding maximization of flow velocity, we have discussed already in previous class. So next, continue with the same. The propellant flow rate, which is steady as well as constant, and the expansion of the working fluid, particularly the chemical products, is and must be uniform as well as steady without gas pulsations or any turbulence, right? The starting, particularly from the nozzle, the flow should be continuous. There should not be no intermediate stop, or there is no sudden pulses of gas injection or gas modification has to be there. Next, the transient effects, particularly during startup as well as start down, are such short duration that have to be neglected. All exhaust gases leaving the rocket nozzle travel with the velocity parallel to the nozzle axis, and this will be my nozzle axis. Now, few more assumptions are the gas velocity, pressure, temperature and density are uniform across any section normal to the nozzle axis. For example, right, if you're considering this as a CD nozzle, right, this is the flow. Now, during this flow, what happens? Basically, the gas velocity, particularly the velocity of any gas, pressure and temperature and density are all uniform across any section normal to the nozzle axis, right? If you're taking n number of sections anywhere, the values, right, the values of velocity, pressure, temperature as well as density are same, right? That we are assuming. Next, the chemical equilibrium, right? The chemical equilibrium is established within the preceding combustion chamber and the gas composition does not change in the nozzle, which also means the frozen composition flow, right? Now, whatever the chemical equilibrium, particularly whatever the fuel plus oxidizer we are burning, right? Any kind of fuel and any liquid oxygen, upon burning you will be getting certain amount of products, particularly any NOx products, any sulfur products, any CO, a few more others, right? And during this, right, when upon combustion of fuel and oxidizer, whatever the composition you will be getting as a product, means as a byproduct of the combustion, that remains same, right? That remains same in complete nozzle system, as well as the gas composition, particularly this product, will be same according to the length of the nozzle. It means there is no change, right? Whatever you are getting out of the combustion is being directly sent out through the nozzle as part of expansion. Now, this particular condition or particular flow is called frozen composition flow. Now, and one more assumption that we are making through is ordinary propellants. Ordinary propellants are stored at ambient temperatures, right? Whereas cryogenic propellants, are at their boiling points. Because let us understand this. Any propellant, particularly fuel plus oxidizer, can be stored at their respective points, particularly storage point, before their evaporation or boiling points. Whereas cryogenic propellants are, let's say for example, liquid hydrogen, right, as well as oxygen, right? These two, we'll just skip the oxygen for now. Hydrogen is a type of cryogenic propellant which is at gaseous state in ambient temperature. Right, which is at gaseous state at ambient temperature. Now, what happens during this? So, if you are putting your liquid hydrogen, particularly in a container, or as liquid nitrogen in a container, out in the open to air system, what happens? They tend to convert themselves to a gaseous form, right? And in order to store the same liquid in a rocket system in a liquidized form, or to have more amount of volume of fuel onto it, what we will be doing? We will be reducing the temperature, right? The temperature within which these propellants are stored to their certain level where their boiling points don't meet. So, as the temperature is very well below the boiling point, they tend to maintain that state, particularly the liquid state. Right? Now, whereas other ordinary propellants, particularly let's say hydrazine or kerosene, right? What happens? They don't convert themselves, particularly they don't change the state from gaseous to liquid. Liquid to gaseous. So, what they will do basically, they are stored at any normal temperature. Can be stored easily, whereas cryogenic required a special area, special cases to hold them together at a specified temperature well below their respective boiling points. Now, based on these assumptions, these permit us to derive a relatively small, a quasi one-dimensional set of equations, right, in order to determine our flow. Right. For liquid propellant or a bipropellant rocket system, an idealized situation postulates an injection system in which fuel as well as oxidizer mix perfectly, means the proportions are in stoichiometric form, so that a homogeneous working medium results, right? And a good rocket injector can closely approach this condition, right? Getting a good stoichiometric ratio is feasible, but getting a good homogeneous working medium, particularly the exhaust products of same form, is somewhat harder. So while injecting the fuel as well as oxidizer, in what way you are injecting, at what angle you are injecting, that determines or that approaches us to the closest form of the condition that we require. Whereas for solid propellant rocket units, the propellant must essentially be homogeneous as well as uniform. The burning rate must be steady in order to have a constant flow, of exhaust products through the nozzle. Now, similarly, for any solar heated or arc heated propulsion systems, which are the trending technologies now, it must be assumed that the hot gases can attain a uniform temperature at any cross section if the flow is steady, because the chamber temperatures are typically high for 2500 to 3600 Kelvin for any common propellants, and all the gases that are above their respective saturation conditions will follow the perfectly gas law. And wall friction losses are difficult to determine accurately because they are usually negligible when inside of the walls are smooth. If we are designing the walls of a nozzle to be some serrated or some curved in nature, at that time we are supposed to consider the wall frictional losses. Now, except for very small rocket chambers, the heat loss in the walls, particularly the rocket, are usually less than 1%, occasionally up to 2%, and for a total energy they can be neglected, whereas the short-term fluctuations in the propellant flow rates, particularly less than 5% of the steady value, are small enough to be neglected. In a well-designed supersonic nozzle, the conversion of thermal or pressure energy into directed kinetic energy of exhaust gases may proceed smoothly without normal shocks or discontinuities. Thus, flow expansion losses are generally small. Now, continuing with the same, we will just glance regarding the thermodynamic equations as well as the relations in order to determine your isentropic flow or the flow through the nozzle. Now, coming to this, we will be understanding first the conservation forms, then we will be deriving the equation. Now, considering the principle of energy, which is readily applied to an adiabatic, right, which is one of our assumption, where no shaft work process is inside the nozzle, and furthermore, in the absence of shocks or friction or negligible amount of forms, flow entropy change in flow entropy is zero. Now, the concept of enthalpy is the most useful in flow systems. The enthalpy H comprises the internal thermal energy plus the flow work, or the work that is being performed by the gas velocity in crossing the boundary. And for ideal gases, the enthalpy can conveniently be expressed as a product of specific heat, Cp, times the absolute pressure, where Cp is the specific heat at constant pressure, which is also defined as the partial derivative of enthalpy with respect to temperature at constant pressure. Now, under the above assumptions, the total or the stagnation enthalpy per unit mass, particularly denoted by H naught, remains constant, that is denoted by H naught equals to H plus V square by 2J, which is again constant. This form where H naught will be your stagnation in enthalpy, right, and H will be your simple enthalpy, right, and this V square by 2J is nothing but half V square into J, which is the kinematic energy or the kinematic force that is being generated. Now, by concerning the conservation of energy, right, applied to an isentropic flow between any two nozzles, axial sections X as well as Y, which shows the decrease in static enthalpy or the thermodynamic content of the flow appears as the increase in kinetic energy, since any changes in the potential energy may be neglected. So, differentiating or having a small difference between those, the enthalpy at section X as well as Y, two sections, what we are getting? The change in kinetic energy, particularly the kinetic energy for a, let me explain. Right, after throat, right, if we are considering any two sections, let's say X, Y, what happens? The enthalpy change, right, the enthalpy change between these two nozzle sections, if we are considering, there will be a decrease in static enthalpy but increase in stagnation enthalpy, because there is an increase of kinetic energy, because the gas which is being generated is on continuously expansion form. So if you are rewriting them in terms of two separate sections, which is hx minus hy, can be rewritten as in this form, where v is nothing but my velocity at that particular section, and which can also be rewritten in terms of temperatures, particularly Cp and Tx minus Ty. Now, the principle of conservatism of mass, right? Now, the principle of conservation of mass in a steady flow for passages in a single inlet and a single outlet is expressed by equating the mass flow rate m dot at any section x to any section y. This is known as the mathematical form of your continuity equation. Now, let's understand this. Right? As per the principle of conservative of mass, what happens? Whatever the mass entering through the section X, the same mass is supposed to exit section Y, which is nothing but a form of continuity. Now, in what way changes, we will see. Now, which can be written in terms of the cross-sectional area and the velocity at which it is passing through, and a specific volume. It means the volume divided by mass within at any section, which can be given as mass flow rate, right? The mass flow rate at section X, which should be equals to section Y, which is also equals to mass flow rate, which is given as AB by V, where A is nothing but a cross-sectional area, V is velocity, the flow velocity, and capital V is your specific volume. Now, a perfect gas law can be written as an arbitrary location at a x is PV equals to RT. Simple as such, where R is the gas constant that is found from universal gas constant R divided by the molecular mass of the flowing gas mixture. Now, the molecular mass of the flowing gas is dependent on what? The products of combustion. The R is constant. The R dash is constant. Now, what varies? Basically, the pressure, the volume, and the temperature. Now, the specific heat at constant pressure, that is denoted by Cp, and the specific heat at constant volume, which is denoted by Cv, and the ratio K are constant for a perfect gas over a wide range of temperatures, which can be related as K equals to Cp by Cv. Again, if you are rewriting those, Cp minus Cv equals to R by J, or Cp equals to Kr into K minus 1 by J. And for any isotropic flow process, the following relations are shown to hold between any two sections of a nozzle. That is, the temperature ratios for two separate sections is equals to the pressure ratios, which is also equals to my specific volume ratios, right? These are related to my two sections of a nozzle taken from the above equations. Now, rewriting the same, and during the isentropic expansion, the pressure drops, right? The pressure drop as well as the absolute temperature also drop is somewhat less. So the specific volume increases when flows are stopped isentropically. Then the prevailing conditions are known as stagnation conditions, which are designated by subscript 0 or O, right? And sometimes total can also be used instead of stagnation. The stagnation enthalpy consists of the sum of the static or the local enthalpy and the fluid kinetic energy. The absolute stagnation temperature, that is T naught, is found from this energy equation, which is equals to T naught equals to T plus V square by 2 Cpj. Right? Now, any data, let me just glance on this. You will be having generalized condition, particularly temperature. In any isentropic expansion, what happens? Sorry. Right? Now, initially, let's say P1, P2, and T1, T2, as well as P1, V2. We'll understand according to these three, right? Now, if you're considering for any nozzle, which is continuously expanding the gases, the products of the combustion, at a section of X, right? What is the continuity equation suggests is basically whatever is entering at the section 1 is exiting at section Y, right? The section Y can also be the end of the nozzle also. Now, considering the absolute values, right? For absolute values, let's say P1, T1 and V1, if in case we want to measure the stagnation, right? There is a change in kinetic energy from X to Y as the gas expands. And during this expansion, what increases? The velocity increases, the pressure decreases, and the pressure decreases, and temperature will also decrease, but in a minor form, right? Now, as the pressure drops, temperature drops slightly, and the velocity increases. And in order to find out the velocity at any particular instance, what we are supposed to do? We are supposed to add up the absolute values with some form, right? With some form, particularly the form for kinetic energy, right? The kinetic energy at that particular section or point is supposed to be added with absolute values in order to get out my stagnation conditions, also called as total, right? In our case, for example, T naught can also be called as stagnation temperature or the total temperature at a particular location, right? And similar to this, where T is my static absolute fluid temperature, and in adiabatic flows the static temperature remains constant. And a useful relationship between the stagnation pressure and the local pressure in isentropic flows can be written as P naught by P is equals to the velocity square into the kinematic form, which also can be rewritten as in terms of specific volumes, where the local velocities are close to zero and the corresponding local temperatures and pressure do approach the stagnation pressure and stagnation temperature. Now, inside the combustion chamber, where gas velocities are typically small, the local combustion pressure is essentially equals to the stagnation pressure. Now, the velocity of sound, also known as the acoustic velocity, in perfect gases is independent of the pressure, which is also defined as A equals to root of KRT, where and a Mach number M, which is a dimensionless flow parameter and is used to locally define the ratio of the flow velocity and local acoustic velocity, which is denoted by capital M divided by V by A. where A, which is again the acoustic velocity, is again rewritten in terms of square root by kRt. Now, the Mach numbers less than 1 correspond to the subsonic flows, whereas the Mach numbers greater than 1 do correspond to the supersonic flows, and the flows that are moving precisely at a velocity of sound would have Mach number equals to 1. At the throat of all the one-dimensional supersonic nozzle, the Mach number must be equal to 1. The relation between the stagnation temperature and Mach number can also be rewritten as T naught equals to T to the bracket of this form, where we are substituting the data towards your stagnation temperature. Now, the previous equation in terms of this can also be rewritten to find out the Mach number as square root of 2 by k minus 1 into T naught by T naught by T minus 1, where T naught and P naught are designation of your temperature as well as pressure stagnation values or the total values. Unlike the temperature, the stagnation pressure or the stagnation pressure during the adiabatic nozzle expansion only remains constant for total isentropic flows. It means there are no losses of any kind. It can be computed from P naught equals to P in this form. Now, the nozzle area ratio, which we discussed earlier, for an isentropic flow may now be expressed in terms of Mach numbers for two arbitrary locations, that is x and y, within the nozzle, and such relationship are plotted with mx, that is Mach 1, right, where ax is nothing but the throat or the minimum area along with the corresponding ratios T by T naught and P by P naught. Now, this is one of the plots that is being plotted with respect to this to find out. Now, this graph shows the area ratio, that is particularly AX by AY, the pressure ratio P by P naught, right, P by P naught, right, and the temperature ratio T by T naught as a functions of Mach number. It means M equals particularly mx by my equals to, right, in a converging or diverging nozzle depicted for supersonic as well as subsonic regions. Now, what happens under this? Mach number 1, what we have studied till now, any Mach number below 1 will be considered as subsonic, supersonic, right? Now, understanding this, and Mach 1, which is the maximum amount of flow, that occurs only at throat. Now, try to understand. So, this particular region separates my sonic sections, particularly CD nozzle, convergent section, and a divergent section, right? Now, in this case, what we'll see is basically, first we'll understand the area ratios, right? Now, what happens to the area ratios? As the area decreases, as we are decreasing the area, I mean we are moving towards in this direction, as the area has been getting decreased, right, you can see the pressure ratio as well as the temperature ratio, right? As the area ratio decreases, the pressure ratio decreases, right, for any flow. Similarly, as the area ratio increases, it means you are diverging from the center to towards the atmosphere. What happens? The area ratio gets increased marginally. Now, during this, there is no limit for your Mach. It goes on increases till the point. Now, these two parameters are dependent basically on the values of K, right? And what is K? Which is nothing but Cp by Cv, right? Now, coming to the next is nothing but what happens to the pressure ratio, right? At a specified point, particularly during a throat, right? For a flow, the pressure will be at here, right? And as it passes after the convergent section, particularly throat, there is a pressure drop, right? There is a pressure drop. But similarly to the same, what happens to the temperature ratio? It also decreases, right? It also decreases, but not as much as my pressure ratio, right? Now coming to your velocity, if you are able to plot on the same thing, what happens? Particularly kinetic velocity, there will be a small velocity decrease, right? There will be a small velocity decrease and a gradual increase of velocity right after the throat, right? As the area ratio goes on increasing. Now, for subsonic flows, right? Any chamber contraction which varies from Y1 or the nozzle entrance ratio A1 by AT can be remain small, and the values which are approaching from 3 to 6 depending on the flow of the Mach number, and the passage is convergent, which has no noticeable effects from the variation of K. Similarly, for rocket motors, the chamber area, that is A1, refers to the flow passage or the port cavity in the virgin grain, right? With the supersonic flow of the nozzle section, which diverges, the area ratio also enlarges, but rather quickly. The area ratios are significantly influenced by the value of K, right? And at Mach 4, the exit ratios, particularly A2 by AT, which has ranges between 15 to 30, are depending on the value of K which has been indicated. But on the other hand, the pressure ratios are less sensitive or to K, but temperature ratios show again more variation. The average molecular mass, which is denoted by M, is a mixture of gases and is a sum of all chemical species in kg moles. It's again multiplied by molecular mass, will give you this, and is divided by the sum of all molar masses, right? So till now what we have to study is basically all the thermodynamic relations that are equivalent or dependent or are needed in order to understand the nozzle flow characteristics as well as the nozzle flow. Now in the upcoming class, what we will be discussing is basically the isentropic flow, and we will try to understand what are the factors that are needed and what are the factors available or dependent to determine the exhaust nozzle flow. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.